All right, thanks, Brett. Back here for a second go around. We're going to go a little deeper in the flow. Today, we're going to look at really some of the deeper integration of how this flow works between the electrical and the software side. So, what we're looking at here is a process, and I'm going to go across the top saying at first, and we're going to do some of the software capability about how we create software architecture from the system model, as well as at the same time, we know in parallel, the EE architect's going to be doing EE platform and topologies. The software developer is going to start building code. The network engineer is going to be understanding the impact to the network and automation of that network, and then taking a look at how we do the integration. So, and we also know, yes, this stuff's got to go back and forth. It is not a one-way process. So even though we're doing stuff early in the design, we know there's going to be impact backwards. Some of this can be done by process. Some of it is done by technology. We support both approaches. So we all have merge diff capabilities in our tools, so we can kind of go back and forth. In some cases, though, we really want to use a process-driven approach where especially earlier in the process, where perhaps the EE architect or the software architect will ask for a change to from the system engineer, and then have that flow down to both sides. So it can get a little complex with large teams on these things, and keeping a straight process model that you understand how you're going to deal with change and impact is extremely important. So let's go through. I'm just going to go through and take a look at these first three areas first. We're going to take a look at, of course, just the systems engineering side of things in the beginning, where you take your requirements and business goals, the constraints for a program, and go ahead and create really a bill of functions, bill of components, and capability around the beginning of a software architecture. So what we're looking at is, it's something that folks don't always understand, because they don't always create the system models quite in this way. But a system model really has a lot of functionality here. So besides creating internal block diagrams and understanding a bunch of different components that I can create and how they might interact with each other, I can also use this to simulate the system. So I can simulate the models that I've created, and I can understand whether the behavior is what I expected. So I can do things like on this one, this is an adaptive cruise control. I can input, enable obstacle, and I can understand what happens when I enable that obstacle. Does the system behave in the manner that we expected it to? So those are the types of things I can do. I can also go through, not only simulate it, but I can test these models. Once I've done a model, I've got sequence diagrams and the like, I can go through and create an automatic test generation format that goes through and says, here are the appropriate tests to ensure that these sequence diagrams are going to work in the way that we think they should. These could be activity diagrams. It can be all focused off your state diagrams. And then you'll see, really what your overall test coverage is on a system model. Now realize this is a system model. There is no code associated with it yet. There's nothing really here except SysML data. So we're doing that, but in the background, we know how to create a test environment and go ahead and test that information. So let's take a look at the next step. What am I going to do from a software architecture perspective? So I'm going to take that skeleton architecture, if you will, for software, and I'm going to start to build out what my software application will look like, what is my model, my APIs, etc. So I'm going to take in a segment of this ACC system, and I can go through and start to create this software. Now, what's interesting is, as I'm building out this model, again, my test cases and everything are going to come through. So we'll be able to continue to do that as we go down into the testing. So we're going into a software developer flow. Do that. So we have a very specific component. You have a state change here between idle, active, and engaged. You have your sequence diagrams associated with it, and then how I can go ahead and update my testing environment from this. So you'll see the testing just on this one small component. But it came over from the system model. So there's continuity from the system to the software architecture down into the software design itself. Well, let's take a look at the next step, which will be going along the bottom flow, and then we'll come back together at the integration layer. Some of the things they're doing, you're doing all these component ICDs I talked about on the first phase of this, and then we have system descriptions, electrical connectivity proposals, and they do a lot of trade studies associated with their domain, just like you would at the system level. They're doing it with another level of fidelity, so they understand weight trade-off analysis and cost analysis associated with how much cabling you put into the system, those types of things. So what we're going to show here is this is the model from Rhapsody. So this is a system architecture model. This is sitting inside of Capital. And inside of Capital, they're going to go ahead and import that model. So I'm just going to scroll through this a little quickly so we can see what it looks like. Now, what this model is, so here's the model that was brought over. It is not identical to the system model because it only comes across with the data that is associated with the electrical domain, electrical and networking domains. And so things like a port is now a hardware port, right? It's not a software port. It's not the exact same thing. It's a wire port. So, and then you can see the two different models side by side. They're very similar. They're developed from the same model, but they are different. And again, based upon what the domain needs, that's what we've brought over. Now, what do they do with that? I know a lot of our ELM customers, you guys are more used to the software side. There's actually a lot of work to do to get this software added into the overall architecture. So what they're doing here is they're going ahead and grabbing that ACC, the adaptive cruise control, and dropping it onto the ADAS controller, and they're seeing what type of performance characteristics they're going to get out of that. Is it appropriate to dump it there? Do I have my CPU, RAM, ROM utilization, and the like? Okay. Other KPIs they can be looking at as well. Then you're going to go through and you're going to do network design. So what happens in here? This is showing a CAN bus in this case, or an Ethernet backbone on here, and showing basically what we're doing with what kind of latency we might be seeing based upon these different functions and running them, and how quickly we're sending those signals back and forth to the sensors and actuators. Okay. Next piece, though, is pretty interesting. This is where I'm starting to put together all the software. Now, in this case, I'm saying AUTOSAR because that's what we have done here. It's an auto example that we have, but this could be a DDS integration, whatever middleware layer you use in your equipment or in your vehicles, you can leverage here. So basically, what I first want to do is take the application software and I want to add that middleware layer to it. For what it is. So this is that abstraction layer that I'm adding in. And in this case, you can see what we're doing with the AUTOSAR abstraction layers, what the ECU is underneath, et cetera. This is AUTOSAR Classic. And then we can go through and run some performance analysis on what we believe that chipset's going to be looking like. So here I'm looking at electrical performance on that particular ADAS controller. And now I'm going to go ahead and do this into a virtual hill environment. So I've done the ECU. I now have what we've modeled here with Siemens was a Snapdragon board. So I've got a virtual hill environment, virtual hardware in the loop environment. So with the Snapdragon board and CAN and Ethernet buses running off of that, so I can actually simulate that. You might go, well, I don't have a Snapdragon model that I can easily use, or whatever your chipset is. There's actually a lot of these types of chipsets that are now available out on like AWS. So there's an ARM set that's out there that, maybe it's only 70, 80% appropriate for what your final chipset would look like yourselves. But remember, we're trying to do this early in the design phase. So the benefits are pretty big when I can do it early in the design phase for it. So again, I'm bringing it through, I'm doing the testing. I can then do running the performance characteristics of this particular board set and see what my electrical performance is. So kind of what we took you through was this, the domain architectures, then down into these different domains themselves, and then what we did with implementation of those, and then finally, implementation of it in a virtual environment, or you could certainly be doing that in a hardware environment as well. So hopefully that was interesting to you. Certainly if there's follow-up, Brett or myself, I'm happy to help.